So last time we used NP reductions to explore how we can establish that various problems such as independent set and Hamiltonian cycle can be rather easily shown to be NP complete. How? Well, we showed that if you could solve independent set or Hamiltonian cycle, then you would be able to solve the satisfiability of 3 CNF formulas, which we had already established, which we also established is NP complete. So this tool, NP reductions, lets us establish conjectured hardness of problems. The subject of today's lecture is what to do about it, in the sense that once you've established that the problem is hard, it doesn't go away. Like presumably the problem came from some need, some algorithmic need to come up with some solution to some problem that you need to solve. So today we'll spend the bulk of the lecture to talk about so-called approximation algorithms. So let me motivate the notion of approximation algorithms by first kind of recapping the process we've been going through to think through the hardness of a problem. So kind of if you want to solve let's say a problem A, the first thing that we've been doing is to say, okay, let's try to show that the problem is in P, or that decision problem associated to the computational task at hand has an efficient polynomial time algorithm. And we've seen many techniques through this course. So you can either try to be creative, you can try to come up with some direct solution, exploiting whatever structure of the problem, or we can reduce it to some other efficient problems that we've seen that have been particularly useful, such as shortest paths, maybe max flow, dynamic programming, linear programming, or any of a number of others. At this point, you have a pretty rich toolkit to try to attack a particular problem. Now, if you succeed, then that's great. I mean, you have an efficient algorithm for it. You may not be happy with the exact running time. You can try to improve it, but at least you know the problem is tractable. If you fail, rather than keep trying until you find an algorithm, maybe there isn't such an algorithm, so it may be wise to try to show that A is NP hard. Okay, for example, NP complete, but maybe it's even outside of NP, or if it's a very hard problem. And for this, you can reduce from some other NP complete problem. For example, from 3-SAT. 3-SAT is a particularly good one because it's the structure of 3-SAT is so simple that it's usually easy to come up with some gadgets that can represent the end of OR clauses with literals. But it could be in some cases some other NP complete problem is the one you want to start from. But the point is that now we have the tools to do that, and that's indeed what we did last time for some graph problems. But if it is indeed NP hard, kind of, let's say if so, if NP hard, what to do next? I mean, the fact that you have established that the problem is NP hard just tells you that you should not be spending your time looking for an efficient algorithm to solve all instances of the problem. But maybe you were interested in this problem to begin with because it came up from some application, maybe at the workplace or as part of some project. So kind of the fact that you established that is NP hard doesn't make the problem go away. You cannot just give up, right? So, so one idea could be to say, well, change the formulation of the problem. Change the problem from A to A prime. Maybe A prime is a little bit more specific, a little bit different. There are different ways to model some specific computation task. But maybe you don't need the full generality of A. Maybe that generality is exactly what makes the problem NP hard. So you can, for example, a special case. And the intuition here is that kind of the proof of NP hardness may rely on abstruse instances that would just are not ones you're interested in. And indeed, that's really the case if you think about the gadgets that we constructed last time to show that independent set and Hamiltonian cycle are NP-complete. We actually constructed instances of independent set and instances of Hamiltonian cycle that looked pretty peculiar, right? So maybe you're not interested in having an algorithm that is going to solve all instances of independent set or all instances of Hamiltonian cycle. Similarly, for the problem at hand, you may be interested just in a special case. So go ahead and formulate it into some problem A prime, and maybe that A prime is not going to be NP hard anymore, okay? So one idea is to just change your problem, okay, as informed by the fact that your NP hardness proof relies on specific degrees of freedom that maybe you want to remove. Another idea could be to use inefficient algorithms for example, in exponential time. So they're not formally running in polynomial time, but mitigate their inefficiency. So again, the fact that you proved that a problem is NP-hard only tells you that it is unlikely for there to be a polynomial time algorithm that solves all instances, but you can certainly try to write down a kind of algorithm that runs in more than polynomial time, maybe n to the log n, maybe 2 to the root n, or maybe 2 to the n, that returns the correct answer. And then you try to say, okay, this is kind of an inefficient algorithm. Can I make it maybe not polynomial time, but the best inefficient with, okay? So maybe use techniques like backtracking or branch and bound that you may have seen in other courses. Basically, you want to mitigate the exponential. And these mitigations may very well make your inefficient algorithm good enough for the instances that you find in real life. Okay? So basically, the idea of number 2 is to say, let's insist on correctness. We're just going to give up on the requirement that the algorithm is both correct and efficient, but we're going to so you kind of so that it can handle instances of the sizes that you're interested in. Somehow, like a complementary idea, which is kind of the opposite of idea number 3, would be to give up on correctness or rather, insist on polynomial time algorithms, but relax the correctness requirement. But not by too much. The idea here being is that you can say, well, look, I'm actually fine with finding a solution that is not optimal or is not the best solution ever. It's okay if it's an approximately optimal solution. It's like not too far, but I want to do it in polynomial time. Okay? So this falls under the category of approximation algorithms. Okay? These are polynomial time algorithms that have provable guarantees on how good the quality of the solutions they return is. This is actually what we're going to talk about today. Well, you see, this is kind of the dual approach to this one. Here it's saying we're going to insist on optimal solutions, but we're going to relax the requirement to run in polynomial time. Here we're saying we're going to insist on polynomial time algorithms, but we're going to relax the requirement of correctness, but we're going to relax it in a way that sort of is still provably correct, in that, or that it's provable. That we know that the algorithm always returns answers that are not too far from, say, optimal. So the one final idea that you can try to use is basically heuristics, right? So basically, you may have no guarantees in either running time or you just try to kind of follow intuition that comes from the data or the structure of the problem. You write some algorithm that maybe like you actually cannot analyze, but somehow empirically it does reasonably well. So all of these are ways that you can try to use to cope with the NP hardness of a problem. Again, you can try to change the problem more, or if you still have to deal with an NP hard problem, you can come up with like a correct but inefficient algorithm and try to come up with the best inefficient algorithm. Or you can take an efficient algorithm that you know it's going to be not correct always, but you try to bound how far from correct it's going to be. Okay? Or you can give up on both and you just come up with some heuristic. So within this landscape of coping with NP hardness, today I want to talk primarily about approximation algorithms. So let's define approximation algorithm more precisely. Specifically, what do we mean by saying that an approximation algorithm always returns an answer is not too far from optimal? So we're going to look up optimization problems. And for the record, today we'll talk about algorithms that return solutions. These are optimization problems. You can form decision versions of these as well, but I'm not going to use that formalism here. But just bear in mind you can frame everything we're discussing also through the kind of decision formalism, not just the search formalism. So an input to the problem is some instance x, okay, in some instance space, and it induces some solution space Sx. Okay, the output of the optimization problem is the optimal solution S star in Sx, which is the one such that the value. So here we induce some solution space and a value function val sub x. Okay, that assigns values to solutions. So what you want to find is the best solution. Let's call it S star, which is the one such that its value is exactly the minimum across all possible solutions as according to the value of determined by this function, value of x. Okay? Now here I'm phrasing the problem as a minimization problem. You can sort of flip everything and phrase it as a maximization problem. Kind of everything is symmetric. So, and it's clear that this formalism is able to represent sort of like whatever optimization problem like you're discussing. So we say that an algorithm, so here's the definition of approximation. So an algorithm A has so-called approximation ratio if alpha is the maximum ratio across all possible instances of the following quantity. On the one hand, you look at the best value. Okay? So this is in the denominator. And in the numerator, what you write is the value of the answer returned by the algorithm. So you say, hey, algorithm, please give me a solution for instance x. And he says, here's the solution. Here it is. Now you look at its value, right? And you want to compare that against the best solution. Okay? The one that an optimal algorithm would have found. Okay? The value of the best solution. And you compare the two. This is a quantity that is always between 1 and infinity, right? Because if you have an optimal algorithm, then this approximation ratio is 1, right? And the goal is you want to find polynomial time algorithms A that have small approximation ratios. Okay, so again, an approximation algorithm has a guarantee that says no matter which instance you're going to give it, it is never going to be more than alpha away from optimal. Okay? And right now, the fact that a problem is NP hard doesn't necessarily tell us that we cannot approximate it well in polynomial time. And if you're fine with an approximate solution, this may very well be a good polynomial time way to get decent solutions to the problem of interest. So approximation algorithms is a huge field in computer science. And people are very interested in understanding for a number of NP-complete problems what kind of approximation ratios can you get. And it turns out that these approximation ratios vary wildly across different problems. So what I want to do now is to give an example of an NP-complete problem where the approximation ratio is actually not so bad. It's going to be actually 2. You know, there's an efficient algorithm to always approximate the answer to within a factor of 2. Which doesn't sound so bad, right? So it makes the fact that the problem is NP-complete less scary. So the problem is called vertex cover. So let's say what the problem is. So the input is an undirected graph. I think I'm running out of juice. So the input is an undirected graph. The output is a vertex cover S. And what is a vertex cover? Is a set of vertices that touches every edge. Okay? And the goal is to minimize the size of the vertex cover, right? So this is a minimization problem. Clearly, it is easy to find vertex covers that are all the vertices. But finding the smallest one, turns out, is a hard problem. So we're going to say claim vertex cover is actually NP complete. Okay, and the proof, I'm not going to go through it carefully, is just to realize that a kind of independent set and vertex cover are kind of dual problems. We already proved that independent set is NP complete. And kind of the way to see that they're dual problems is that S as a subset of V is an independent set if and only if V minus S, so its complement in V, is a vertex cover. And so that kind of this maximizing an independent set or minimizing a vertex cover is basically the same thing. And let's just go through both directions of the statement. Suppose that S is not an independent set, so it means that there exist two vertices in S that share an edge. Well, when I take its complement, it means that there will be an edge neither whose vertices are contained in this set, so it's not a vertex cover. Conversely, if this set is not a vertex cover, that means that there is an edge neither whose endpoints appears in this set. When you take their complement, you will get a set where there are two vertices that share an edge, which means it's not an independent set. Okay, so this really is like an if and only if. And this tight kind of relation between vertex cover and independent sets and the fact that independent set is already NP-complete tells us that vertex cover is NP-complete. Okay, and maybe just I'll put here the diagram that we had last time. We showed that everything goes to C-set, C-set reduces to SAT, SAT reduces to 3-set, and 3-set reduces to independent set, which now we know also reduces to vertex cover, and 3-set also reduces to Hamiltonian cycle, right? That was kind of the map from last time. All right. So here we have is a NP-complete problem. So now we're going to prove that a vertex cover has a pretty simple two approximation algorithm. Theorem, so vertex cover has an approximation algorithm with approximation ratio alpha equals 2. Okay, so maybe you could think 2 is large, but 2 is definitely not that large. I would say it's pretty small. And it's great that in polynomial time you can provably always obtain a vertex cover that is at most two away from the optimal one. So that's the theorem that we want to prove. So the idea of the proof is we're going to connect vertex cover to matchings. Okay, we're going to leverage connection between vertex covers and matchings. And then the algorithm will basically look for a matching with a certain property, and then out of that it will cook up a vertex cover that by construction cannot be too far away. So here's the basic, so there are two basic claims. So let's look at the first one. Let me also remind you, we already came across matchings, but what is a matching? Is a set of edges where no pair of edges share an endpoint. Okay, so it's kind of the edges are kind of disjoint. If you kind of plot them, or if you look at them in a drawing, they don't touch one another. Okay, these are kind of separated edges. So the claim we're going to prove is that if S is a vertex cover, and M is a matching, then we know that the number of edges in a matching is bounded by the number of vertices in a vertex cover. Okay? It's actually like a reasonable proof. So again, like we've put no relation. I'm just saying S is a vertex cover, M is a matching. God knows where they are in the graph. But we're saying no matter what, the size of the matching, number of edges in the matching, is bounded by the number of vertices in the vertex cover. Okay? So why is that? Well, let's see. So for every edge E in the matching, there exists a vertex V in the vertex cover that only touches E and no other E prime in M. Well, why is that? Well, because, look, a vertex cover touches every edge. So in particular, I can just look at one of the endpoints of this edge. Could it be that there is, when we look at a different edge, we actually find the same vertex as one of the endpoints? No, it cannot be, because in a matching, edges are not supposed to share endpoints. Okay? So it really must mean that when you look at the number of edges here, for each of the edges, there is like a distinct vertex in here, either of the endpoints that you will find. Okay? Maybe not both endpoints, okay? But at least one or two endpoints will appear here, and that very same endpoint cannot be an endpoint of any other edge. Okay? So this means that indeed the number of edges is at most number of vertices in the vertex cover. Okay? In particular, we learned that the size of the maximum matching is bounded by the minimum across all vertex covers, okay? Because it's true for all matchings in vertex covers. So in particular, I can just look at the largest matching and the smallest vertex cover. Okay. All right. So here's the second claim. So it's called claim 1 and claim 2. Claim 2, suppose that you have M is a so-called maximal matching. This is not a maximum matching. Maximal means that it cannot be extended further. Meaning that there exists no other edge in the edge set that could be added to the matching to make it bigger. Okay? So if you have a maximal matching, then S, which is the endpoints of edges in M, so take the matching, look at the endpoints of all the edges in it, then S defined in this way is a vertex cover. Okay? So in other words, there is a way from any maximal matching to construct a vertex cover. Just take the endpoints of the edges in the matching. The proof is also pretty simple, that if S is not a vertex cover, then there exists an edge in the edge set that has no endpoints in S. Okay, that's what it means to not be a vertex cover. But in such a case, we could add the edge E to M, right? Because S was constructed from the endpoints in M. Now here's an edge, neither endpoint of which appears in S. But that means we can add E to M and still get a matching. And this kind of contradicts the maximality of it. So we are using the fact that it was a maximal matching. Okay? Now notice that the size of S is exactly 2, right? Because in a matching, no edges share endpoints. when you consider all endpoints, you're going to get a set that is 2 times the number of edges, okay? Because kind of endpoints don't repeat. Okay, so we have a way, given a maximal matching, to cook up a vertex cover of twice that size. Okay, these 2 claims together immediately give an algorithm. So the proposed algorithm works as follows. Find a maximal matching, M tilde, in the graph, and then the output the set of vertices that are the endpoints of the maximal matching. Okay? So we're about to analyze it, but let's just realize that this first step is pretty easy. How do you find the maximal matching? You do it in a greedy way. You just put in an edge, and again put in an edge, put in an edge. As long as there are edges that you can add, you throw them in. You never look back. At some point you get stuck, but that's okay because you have a maximal matching. Okay? So this is the proposed algorithm. It's clearly a polynomial time algorithm. So all we're left to do is to argue about how good of a vertex cover does it always produce. Okay, well, let's see. So we need to prove that the approximation ratio is 2. So first, let's notice that the maximal matching is at most, as we remarked earlier, the minimum vertex cover. And minimum vertex cover is certainly no more than the size of the vertex cover that we construct, this one. Let's call it S of M tilde. And S of M tilde, because it's constructed in this way, is exactly 2 times size of M tilde. Okay? Well, if that's the case, then our algorithm always returns a vertex cover of size 2M tilde, and we want to compare that against the best vertex cover. Right? So this is, again, our algorithm always returns something that is 2M tilde, and we want to compare this. How far is it from the best vertex cover? Let's see. Certainly, this is no more than the ratio of 2M tilde and the maximum matching, right? Because this is only smaller. So if I replace the denominator and make it smaller, then it can only go up. And if the maximum matching is certainly at least as big as a specific matching, M tilde, right? The specific maximal matching that I found can only be smaller. So this makes this ratio bigger, and that's 2. So this proves that on every instance, our algorithm returns a kind of an approximation ratio. I mean, the solution is never more than 2 times away optimal. Okay? So this is a cute, efficient algorithm that we can provably establish always returns an answer that is not too far from optimal, despite the fact that the algorithm is NP-complete, that the problem is NP-complete. So this is clearly, like a better than nothing. Okay. Does it mean that every NP-complete problem can be well approximated? That would be nice. It turns out the answer is no. So next we will see at an example of a graph problem that it is extremely unlikely that we can approximate it within any efficiently computable function. So it really is among the hardest to approximate. Okay? So that's what we're going to look at next. So we're going to look at the traveling salesman problem. It may or may not have already come up in some homework. I'll still define it. So the input is a undirected graph, G, and distances. So every edge has a distance. The output is a tour. I don't know, let's call it T. Okay. What is it? It's just it's really a cycle. What is it? It's a cycle that visits each vertex once. Okay? And the goal is to minimize the length of the tour. Okay? So we look at all the edges in the tour, and we look at their lengths. Okay? So why is it called the traveling salesman problem? Because the idea is that you have, what you should keep in mind, there is some cities are connected by roads. You want to visit, you want to start from a home city, travel to all the cities exactly once, come back to your home city, and you want to travel the least amount. Okay? And the graph basically gives you the options of how you can travel between cities. So we're going to prove something pretty strong, for instance. We're going to start with something maybe not stronger, then we'll make it stronger. We're going to say that if TSP has an approximation algorithm where alpha is 2, then P equals NP. Okay? So we don't believe that P equals NP, so therefore we should not believe the traveling salesman problem can be approximated with an approximation ratio of alpha equals 2. Okay? So this is an instance of a paradigm called hardness of approximation. The other side of the study of approximation algorithms, you could either try to design approximation algorithms and say that, oh, look, here's an efficient algorithm that gets me alpha close to the solution. Or you can try to look at the hardness of it and try to prove that unless P equals NP, there cannot be an approximation algorithm with a particular alpha for a particular problem. Okay? Notice there's something cool happening here, right? Like a priori, the question P versus NP should have potentially nothing to say about approximation algorithms. It's really about optimal solutions. Yet, it turns out that it does. And you can base many hardness of approximation results on this assumption that P not equal NP. So let's look at this. This claim is actually not complicated. Interesting and deep, but the proof is pretty neat and not complicated. So the proof, we're going to show that is an algorithm that approximates TSP alpha equals 2, then we can solve an NP-complete problem, Ham cycle, which we saw last time, exactly. Notice we started with an approximation algorithm with a certain approximation ratio, and from it we cook up an exact algorithm to solve Hamiltonian cycle. Now, because Hamiltonian cycle is NP-complete, this would imply that P equals NP. Okay? So what's the idea? So we're going to do a reduction, okay? Except that now, kind of the core of the reduction, rather than being an exact algorithm, is an approximation algorithm. And the idea is that we're going to try to amplify, we're going to construct an instance of TSP that if you have a good enough approximation algorithm, if you have good enough solution, then it will tell you something about a Helm cycle instance, okay? So remember, the Helm cycle doesn't have distances, right? A Hamiltonian cycle just says, give me an undirected graph, period, no distances, and find some cycle that visits each vertex once. I don't care its length, just is there one, right? In TSP, there are distances. So let's say that we are given a graph as an instance of Hamiltonian cycle. And maybe it looks something like, I don't know. Okay, maybe it looks something like this. Again, there are no distances, nothing. So we're going to modify this by adding. So first we're going to say that for each edge in G, we're going to label it with this 1. So we're going to say, okay, this edge already is part of the graph. 1, 1, 1, 1, 1. Put a 1 everywhere we have an edge. Okay? Then we're going to say, look, for every missing edge, namely some edge that is not in the edge set, among all possible n squared edges, label it with a distance that is 2n. Okay, so for example, look, this edge from here to here is not part of the graph, so I'm going to add it, but I'm going to label it 2n. Okay, so this is a new edge that I'm adding. For example, the edge from here to here doesn't exist, so I'm going to put it here, 2n. Okay? What else do we have here? For instance, this doesn't exist, so I'll put it. Okay, and so on and so forth. Like, I'm not going to put some of them, but you get the picture. So of all the missing edges, among all the possible edges, I put them in and I label them very expensive, 2n. So now, what's the point? If G really did have a Hamiltonian cycle, then G prime, the new graph that I've constructed with these distances, n, right? Just take whatever Hamiltonian cycle you found, call that a tour, and because it uses existing edges, you will have 1 plus 1 plus 1 plus 1 up to n times. So the new instance of TSP has a tour of length n. If G does not have an Hamiltonian cycle, then all tours on the new instance will use at least one edge that didn't exist. And that edge will have weight 2n, right? Then any tour on G prime has length at least 2n plus, and in the best case scenario, all the other edges are already existing, n minus 1. Okay, so this is 3n minus 1 overall. And the point is that I can distinguish between the two cases with an approximation algorithm that has alpha. The approximation algorithm can distinguish between the two. I have amplified, I've constructed an instance such that if there is a Hamiltonian cycle or not a Hamiltonian cycle, then the tour on one side is pretty small, and in the other case, all tours are pretty big. So it's okay to only try to solve the TSP with an approximation algorithm with good enough approximation ratio. Okay? So this is a way to solve a Hamiltonian cycle, and it sort of proves the theorem. Now, an interesting fact is, why did we specifically put 2 here? What if we put, I don't know, say instead of 2, we put 10, okay? 10, 10, 10 everywhere. Then we could have said here 10, right? So actually it strengthens our result. Instead of saying 2, we could put 10. But wait, why did I put 10? Why not put n, or like n squared, or maybe even 2 to the n? Now it turns out that this very same construction works for any alpha n that is polynomial time computable. So this is saying that TSP is really inapproximable. As long as there's an approximation algorithm with some alpha of n, where alpha of n is polynomial time computable, this includes 2 to the 2 to the n, for instance, okay? No, this includes 2 to the n, for instance. Then p equals np, okay? So this is very much unlike vertex cover, where in vertex cover we definitely had an approximation algorithm with alpha equals 2, whereas here, like, there exists no small approximation. So this problem is also NP-complete, but it behaves under approximation algorithms very differently. This is kind of among the hardest to approximate. Okay. So that's as much as I wanted to say. Remember is that you either want to design them or you want to rule them out, just like normal algorithms. And just like normal algorithms, they run in polynomial time. And just like normal algorithms, you need to prove their guarantees. Now, sometimes you may not even be able to come up with approximation algorithms, and I'll just briefly a little bit about sort of a heuristic approach. This is something that you may be very familiar from other courses, especially ones that have to do with continuous optimization. So, so let's talk a little about heuristics. Again, for say maximization problems. And something similar holds for minimization problems. So for example, a common problem is that you're given some real function, let's say from reals to reals, and want to find the maximum function if it exists. Okay, so if it's unbounded, then it doesn't matter. Now, one potentially idea you could say is to, try random volumes. That doesn't seem to be like such a good idea, right? So it will take probably a while for you to find a maximum. So the idea that you're probably more familiar with is the idea of hill climbing or gradient ascent. Roughly, the idea is that you're going to start at some random point, and then you're going to repeat, some number of times, maybe 10,000 times. And again, this is a parameter that is part of the heuristic. And you're going to pick some x prime that is like some neighbor of the current x. And if the value of the neighbor is better than the value of yourself right now, then you set your neighbor, then you set your current location to be the neighbor. This is kind of like the template of like gradient ascent. This is saying, look, I'm just going to move in a direction, the value of the function, but the value here is f, where the value of the function looks bigger. The intuition being is that if and your starting point was here, then you're kind of moving up, moving up, moving up. And when you get to the top, even though if you keep running the algorithm, every other value you're going to consider will be smaller. So you're just going to discard them and always stay up here. Now, of course, the function need not, okay? The function may have a local maxima, right? So it could be that you get stuck here. Or it could even be much worse than that. Maybe your function looks nothing like that. It looks something like this, where this algorithm is going to perform very poorly. So in practice, there are sort of refinements of hill climbing, something called simulated annealing, that tries to at least handle things of this sort. Okay, whereas functions that look like this, there's not, a whole lot that you can do in a general case. But there's a refinement of gradient ascent called simulated annealing. I'll write it down now. That performs pretty well in practice, and so in other courses, there are theoretical explanations how these things work. If you assume certain things about f, has to be sufficiently smooth, has to be convex, and things of that sort, or kind of almost convex. So I'll just mention this idea of simulated annealing. This is an idea kind of inspired from physics, where, again, you start with some random point, and you have some outer loop that, again, is like a parameter you have to empirically find, some number of times, let's say 100 times. It could be 1,000 or 1,000,000 or 5. And you repeat, again, some number of times, let's say, again, 10,000 times. Something similar, but not quite the same. So we're going to set x prime to be the neighbor, some neighbor. Maybe it's usually chosen probabilistically in some not too far away from it. Like before, if your function is better, then you're just going to move there because you have improved your situation. But if instead, otherwise, even if it is, even if the neighbor is smaller, with some probability, that this is kind of like the temperature, we'll talk about it in a moment, with some probability that is modulated by just how much worse really is the other one. So if it's much worse, then this probability is going to be very small. If it's just a little bit smaller, then this probability is going to be slightly bigger. You're still going to change. You're still going to say, even if it's a little bit worse, with some probability, I'm going to go there. So this is the algorithm. And what are these PIs? These are for the outer loop. This is called the temperature schedule. And basically, you start so-called hot with a large P. So this increases the probability that even when you see a value that is smaller than the current one, you might still go there. And as you go through the outer loops, the temperature decreases, and this decreases the probability, and you look more and more like climbing. What is the intuition? The intuition is that hill climbing might just get stuck on a local optimum, for instance here. But simulated annealing, at the beginning of the algorithm, in the first few iterations, there's still some probability that this thing might decide, you know what, I'm just going to continue here, here, and here, because the temperature is still high, and there's still a reasonable probability I pick a neighbor that is smaller than me. And if I do that, then I might have a chance to go up to the real optimum, the real maximum. And by that time, the temperature will have cooled more, and I'm less likely to make my way down again and lose the optimum. Okay? So simulated annealing is kind of like a heuristic to try to shake yourself that you might have just gotten stuck on using hill climbing. Now, these are heuristics. I didn't say anything about proofs. In fact, all of this is incredibly informal. In the continuous domain, there are all kinds of things you can try to go ahead and prove using techniques that are kind of not part of this course. And optimization is a very large field in which you can take classes, and things like gradient ascent and its many, many variations are something that people are going to study a lot. Anyways, this was within the context of NP completeness. Today, we looked at two ways to cope with it. One is approximation algorithms, and the other one is heuristics. And this lecture concludes the unit in this course about computational complexity. And next time we start a unit having to do with, I think, sketching and streaming algorithms.